Okay, first part you guys have is the kinetic molecular theory, and there's 5 assumptions, and it is assumptions that are of gases. So these are all of gases. So the first assumption, that gases consist of large numbers of tiny particles that are spread out far apart relative to size. Oops. Number 2, collisions are elastic. Meaning there's no net loss of kinetic energy. Next one, gas particles are in constant rapid random motion. This is where the diffusion and effusion come into play, because they're in constant rapid random motion. The fourth one, no forces of attraction and repulsion. And number 5, the average kinetic energy is directly related to temperature. So as temperature goes up, the kinetic energy goes up. Temperature goes down, kinetic energy goes down. Questions on any of those? Okay, number 2, the second one you have is properties of liquids. Wait, okay. Can I switch it? So liquids have a relatively high density compared to gases. They're about 1,000 times denser than gases. So very high density when comparing it to gases. They're relatively relative incompressibility. So compared to gases, their particles are a lot closer together, so it's harder to compress them. You can compress it a little bit, not very much at all when you compare it to gases. Surface tension is one of their properties. What is surface tension? Right. So there's forces acting on the surface molecules, pulling them towards the center, which is why water beads up. Especially on like on your desk, if you put a little bit of water, it'd bead up because their forces are pulling them inward. That's why water bugs are able to skim across the surface of the water, because there's some surface tension there, and they are light enough and that they don't break that force. They have capillary action. Oops. Reaction. Do you guys know what capillary action is? Do you guys know what a capillary tube is? Yeah, you use it when they prick your finger and then they just put a little glass tube up to your finger, and what happens? It goes right up the capillary tube. Do they actually suck it up though? No, it's the attractive forces between your blood and the glass that's pulling the blood up the glass tube. This is also why you see a meniscus on, like when you look at a graduated cylinder, you see a little meniscus at the top when you're taking, you guys remember what the meniscus is, right? Okay. They're adhesive properties. Now some liquids, yeah. But some liquids, though, they are not attracted to the glass, and so they have an opposite. Meniscus is concave. They'd have more of a convex surface, like mercury. If you put mercury in a graduated cylinder, it'd have a convex surface because it's not attracted to that glass at all. It's actually repelled, so it goes down instead of up the glass. And then viscosity. You can have highly viscous liquids and low viscous surface liquids. What is the difference? What's viscosity? Yeah, corn syrup to water. It's they define it as the resistance to flow. So if you were going to try to pour it out, which one resists flow more? It would be highly viscous, like corn syrup, versus water. Be easy to flow. Yep. Properties of solids. There are two types of solids, two basic types. Crystalline and amorphous. Crystalline and amorphous solids, what's the difference? Crystalline has a crystal structure. It has very rigid geometric form. There's actually 7 geometries it can form. We didn't talk about those. Cube is one, though, like salt, sugar, maybe crystalline. How about amorphous? Yeah, sand is more of a crystalline. Probably a metal, yeah. Glass is an example. They're just random mixing, like there's no pattern to the molecules within the solid. Glass is sometimes called a supercooled liquid, actually, or some amorphous solids are called supercooled liquids because they actually over time will flow. Old glass windows, if you look through them and you can kind of see waves through them, it's because the glass is thicker in some parts because gravity is pulling it downward. So it's actually flowing over time, but very, very slowly. They have a definite shape and volume. Definite melting points. Very high density when you compare it to gases. Now, remember, water is an example of one where the density of the solid is actually less than the density of the liquid. That's unusual. And then incompressible. Their particles are the closest together between the 3 phases, so it would be very incompressible. Okay, molar enthalpy of vaporization and fusion. So molar heat of vaporization is delta HV, and that is, it's a V. Yep. So it's the energy required to convert 1 mole of liquid into a gas or gas to liquid. I put a double-sided arrow there because it's either way. Delta HV is the energy required to convert 1 mole of liquid solid, or vice versa. Convert 1 mole of liquid to a solid, or 1 mole of solid to a liquid. The units for these are always is a kilojoule per mole. And so we use conversion factors where you would convert moles into kilojoules using a railroad track. They might even give you grams, so the first thing you have to do is convert grams to moles, and then you can use delta HV or delta HF to convert to kilojoules. I will give you any of the vaporization and fusion values that you need that changes based on what substance you're dealing with, and they're constants. So I'll give you those, whatever you need. You just have to be able to use it correctly. Any questions on delta or the molar enthalpy of fusion or vaporization? Okay. Next, phase diagrams. So let's draw one here. And this would be pressure versus temperature. And they look kind of like this. And this is where the substance is a solid, this is where it's a liquid, and this is where it's a gas. What is this point right here called? Triple point. Triple point, where all three phases at that specific pressure and temperature, all three phases coexist. Okay. You would have a solid, liquid, and gas phase, all of that, in the same container. Yep. Okay, if we cross this line right here, what phase change is occurring? Melting. We're going this direction. If I go this direction, freezing. What about right here? No. Yeah. What do you mean? Up here? Gas to solid? Yeah. What's that called? transition to sublimation.
Okay, so both of what are both of those little like branches gases?
No, just in between here, it's a gas.
Oh.
So in this area, so at this pressure, from this temperature up to, well, it's always then gas at that point. There is a critical point where if you're past that critical pressure and past the critical pressure or temperature, it'll always just be a gas. So there's a critical point there too. Okay. You can use this to find like melting points and boiling points. So let's say we want to know at the melting point at this pressure, what is the melting point? So I would come across and come down, and here's the melting point right here, this temperature. And it looks, I mean, it looks like that. This is not drawn to scale or anything, so. You guys have any questions about the phase diagram? I thought there's a way I can. Put it. I don't know. Can I clear it? Okay, and then next you guys have Boyle's Law, right? Oh, converting pressure units first. Oops. So that's, I will give you, just like on the quiz, 1 ATM is equal to 760 millimeters mercury. Yeah, I will give you this. But then you have to be able to do the conversion part. Okay, and then you have Boyle's Law, right? Oops. So this is P1 V1 equals P2 V2. And then Charles' Law. And I'm not as concerned that you know which one's which, just that you know how to do the calculation with it. And this is Gay-Lussac's law. And then the combined gas law. And I will give these to you just like I did on the quiz, okay? It does not matter what the pressure and temperature units are. You can use ATM, you can use millimeters mercury, as long as they're the same on both sides, because you need the units to be able to cancel out. Temperature, though, needs to be in what units? Kelvin. Always for gas laws, they have to be in Kelvin. And how do you convert it to Kelvin? Add 273. Very good. I will give you those equations. Okay, ideal gas law. This is where we'd have PV equals nRT. I will give you R. This is the ideal gas constant. I will say that I'll put on the sheet that the ideal gas constant is equal to 0.0821 liters times ATM over moles Kelvin. You'll have to remember that that ideal gas constant is R. What did N stand for? Moles. And then because we have R in this equation, pressure has to be in what units? Because of the units that R has to be in ATM. Volume has to be in what units? Liters. And then temperature is always in Kelvin. So it doesn't matter what units we had before, like in the combined gas law, because R is not a part of that law, that equation. But whenever you have R in your equation, then you have to use these units. Okay, density and molar mass. We had those two equations. Density was PM over RT, and molar mass was little m RT over PV. What's big M stand for? Molar mass. And little m was just mass. Like if they say you have 2 grams of this gas, what's the molar mass or something? That would be the mass part, the 2 grams. Now, both of these, you really don't need these equations. This is just a one-step way to solve it, but if you want to use the ideal gas law, you can still get the same answers, the correct answer.
What do the variables stand for?
D is density. I guess big M is molar mass. And then R and T is the ideal gas constant and temperature. But both of these have R in their equations, so you need to make sure you have pressure and volume in the correct units. I will probably, just like on the quiz, have where you need to write out your givens and unknowns, like P equals this, V equals this. That way, well, and then the equation that you're going to use, and then your answer. I can give you some partial credit a lot easier that way. I can see if you can show at least some of your work. It gives you a way to get some credit. I can see where, if you did get it wrong, where you went wrong, instead of just writing down numbers, organizing your work a little more. Do you want to do any sample problems or go over anything else, questions over anything?